you can hear. So I think that without the mic, Cynthia would not be able to hear questions. If you have questions, wave and I'll bring the mic. Good. So in a better world, Cynthia would be here and giving the talk in person. But as things are, Cynthia will tell us about measuring our chances, risk prediction in this world and its betters.
Thank you, Omer. And I have really been enjoying zooming in and listening to some of the talks. They've been fantastic. This workshop has its roots in the theory of algorithmic fairness. And you've been using the word fair in lecture after lecture after lecture, but we're losing track a little bit of some kind of gut feeling of fairness or equity, and this has been on our minds. So here are some examples of risk prediction. On the left, we're scoring somebody in power, someone who, so this is sort of indirectly related to equity because we're scoring the judges on what might be inequitable behavior, but we're not really concerned about our scoring function being unfair. And on the right, we have two very different kinds of examples. On the top right, we're predicting something that at this very moment, we cannot affect. Absolutely no way to affect it. And so inequity is not an issue in this scenario. But in the second case on the right, the lower one, inequity is, deeply involved in this question. So just kind of keep that in mind as we briefly review some of the setup. The thrust of a lot of work has been to view accuracy as a kind of fairness. And we even tend to call PI star nature as if it's kind of fixed and embedded. But chances of success are very often contextual. So somebody's chance of success in a workplace may depend on whether the workplace is egalitarian or misogynistic. And in fact, even who we are, our feature vector, the way the information about us that kind of is fed into the predictor is also contextual and deeply related to questions of equity. So whether in developing we had clean air and water and good housing and good education, our parents' connections, what kind of healthcare we had access to, all of this sort of deeply affects who we are. So in the rest of the talk, I'm going to use the notation that has been used often in the last couple of days. PI star is the real life probability, but I'm not going to call it nature, that I will receive a positive outcome. OI star is a Bernoulli draw from PI star, which is the real life outcome. And then we have the modeled probability and outcomes drawn according to the model with tildes on them. Okay. And in case you've been unconscious for the last 4 days, outcome indistinguishability for predictor F says that given a distinguisher collection A, no distinguisher in the collection should be able to distinguish real life outcomes from those drawn according to F. And as Michael explained, there's a hierarchy, and we're going to be looking at the second level, the sample access OI, in which our distinguisher has access to the prediction. Okay. So kind of the reason we're all here is that outcome indistinguishability, outcome indistinguishable predictors can be constructed given only real life outcomes data. So if there are outcomes from real life, samples of the form IOI star, then there's an algorithm for creating a predictor that is outcome indistinguishable from this real life. And the key point here is that we're only working on outcomes data. The predictor never sees, the algorithm to build P tilde never sees the values P star of X. And we don't even know whether these values are necessarily integer, or whether there's actually uncertainty in the world, and P star of X could be a number between 0 and 1. Okay. So our starting point is the fact that outcome indistinguishability is descriptive. It's not aspirational. It's not trying to get us to a better world, like changing the fundamentals of how success should be viewed and encouraged. And so we want to think about something that we're calling corrective transformations. So that's our topic. How do we get towards a better world? Or suppose we had an idea of what would be a way of getting to a better world. What can we do about it? So imagine first that we have a utopia. And in this utopia, every individual is completely supported to reach their full potential, and they have adequate health care and so on and so forth. So that's our utopia. And so each X has some U star of X, the utopian chance of success. And then real life kind of beats it all out of us. So in real life, we have all kinds of horrible isms. We have sexism, and we have racism, and we have pollution, and we have inequity, and we have lack of gender affirming care and lack of access to reproductive care and so on. And people's ability to succeed can be distorted, usually for the worse, and sometimes because of privilege, made for the better. So we imagine that there's this horrible transformation T that takes our utopian world and beats it down and gives us what we actually have in real life. And this might be a transformation that completely destroys information. And there may be no way, information theoretically, to get back from X prime to X, or even from P star of X prime to U star of X. So our starting point is the notion of a transformed predictor. We can think of the predictor as a vector of dimension of the size of our universe, and it's indexed by elements in the universe. And the transformed predictor is another vector of the same length with different probabilities. And tau, this transformed predictor, operates on pairs on X P of X, producing the transformed predictions tau P of X. Okay. So these notations are completely equivalent. And sometimes it's just nice to spell out the P of X, and sometimes it's nice not to have to bother. And in particular, if P star is kind of what's happening in real life, or in one particular context in real life, we can imagine a transformation that operates on P star and gives us a transformed predictor. And this is mathematically well defined, although of course we can't get our hands on these numbers. We can't even get our hands on P star of X. So, and we don't even know if P star of X has to be integer or not. So, but it makes sense sort of mathematically. So to give you an example, suppose in the first example, in a transformed world, scores for members of some group G are boosted. Say, add 0.2 to the scores of members of G. So formally, that would say that tau pi of X is just the min of, tau of P of X is the min of P of X plus 0.2 and 1 for X in G, and just P of X if X is not in G. So we're only playing with the values of people in G. Now, that's the most simple kind of transformation, but another kind might be parametrized. So tau might be paired with a learner that learns the values of the parameters by studying real life outcomes data. So we have a learner L, and it gets samples from the real world, and it produces some parameters pi. An example of this is that in the transformed world, scores for members of a group B are adjusted to ensure demographic parity, i.e. that the probability of a positive outcome will be the same for a random member of A as for a random member of B. So the way that's done is by learning the base rates of a positive outcome for members of A and members of B and computing this value pi. And then we can set tau of P of X to be P of X if X is in A, stays unchanged. And then this convex combination of alpha and, I'm sorry, that should have been pi and 1 minus pi times P of X if X is in B. So that's a case where we have some parameters that we learn. Now, there's some uncertainty here. You notice that we have a learner, the learner gets samples. Those samples are drawn from a distribution. If we run the learner at different times, we may get slightly different values. So it's not even clear necessarily how do we fix the specific tau of P if there's a learner involved. And so there's a technicality, which is that we define something which we call the canonical transformed predictor. And it's well defined. We're taking the expectation over the randomness of the samples fed to the learner, coins of the learner, and any other randomness. But now that I've told you about that, we're going to forget about the canonical transformed predictor because it's just, it won't add to our intuition. Okay. So where does tau come from? Well, it's exogenous. It might be the combination of experts and wisdom and ethics and policy and history and geography and arithmetic and machine learning and so on. And for the purposes of this talk, just assume that it has been determined that for one reason or another, we would prefer the world Q star, which is defined to be tau of P star. The transformed world would be a better world. So our corrective transformation is the world of Q star. And we would love to be able to find Q star, but of course, we have no data from this world. And in some sense, so our question is, when can we build a predictor Q tilde that is indistinguishable from this better world Q star using only real life samples? So we have this transformation T that took utopia and moved us to P star. Tau applied to P star will get us to a better world. No reason at all to think it gets us back to utopia. T was information destroying, but it's still a better world or a better work environment. So we have real life samples from P star. We know that we can build predictors that are indistinguishable from P star. We'd love to be able to do the same thing on the right with Q star, but we have no data from Q star. We have no samples of Bernoulli drawn according to Q star of X available to us. And so what we're asking is, can we even build a Q tilde that is indistinguishable from tau of P star using only real life samples? And if so, when or what are the conditions? So in order to answer this, we need the notion of a random instantiation of a predictor. Remember that our predictor is a vector of dimension size of the universe. And for every X, we'll let P prime of X be a draw from the Bernoulli distribution with parameter P of X. So P prime of X is necessarily Boolean, whether or not P of X is Boolean. Okay. Now, if P is always Boolean, there will only be one random instantiation of P. It's exactly P itself. But if P is not sort of uniformly Boolean, there can be many possible random instantiations of P. Okay. And it turns out the key property for enabling us to learn something that is indistinguishable from Q star, from our better world, is the notion of robustness. The robustness of the transformation tau to random instantiations. Essentially, we're looking at the following question. In general, does tau of P look like what we would get if we chose first P prime as a random instantiation of P and then looked at tau of P prime? So let's just kind of look at this pictorially. On the left, we have X. This is on the left, we have the world of P. And so P of X is just some value V. And if we look at the random instantiations of P prime of X, we get, say, U1 for the first random instantiation, U2 for the second, U3 for the third, and so on. And we know that on average, they're equal to V. That's just the properties of the Bernoulli. So now, suppose that tau of P applied to X is some value V prime. And we're asking, is it also the case that when we look at random instantiations of P and look at what tau does to them, and we get these values, U1 prime now, U2 prime, and so on and so forth, will these average to approximately V prime? So if this holds for most X, then tau is robust to random instantiations. And if it doesn't, then tau is not robust to random instantiations. So again, robustness to random instantiation says that tau of P looks like tau of random instantiation of P in expectation. So going back to our examples, in the first one, we boosted scores for members of G. And this is not robust to random instantiations. So to see this, suppose the members of G all have P of X equal to a half. And so here on the left, P of X is a half, and P prime of X is 0 or 1. About half of them are zeros and half of them are ones in the satellites, the UIs. On the other hand, if we look at what's going on the right, tau P applied to X is 0.7. We took 0.5 and we added 0.2 to it. But on the random instantiations, well, half of the random instantiations were already 1. And so we can't add anything to them. The other half of the random instantiations are 0, so we can add something to them. And so what we end up with is that we get 0.7 for tau P of X, but we get 0.6 for the average of tau of P prime of X over the different P primes. So this is not robust to random instantiations. The demographic parity example is robust to random instantiation. And in a nutshell, this is because with high probability, a random instantiation of P will yield approximately the same value for pi. So when you're estimating your base rates on the random instantiation versus on P, you get the same thing. And what we find is that robustness is a complete characterization. So informally, if we have a transformation tau together with a learner L, if L comma tau is robust to random instantiation, then there's an algorithm M for learning a Q tilde, which is outcome indistinguishable from Q star, for any set A of sample access or no access distinguishers. On the other hand, if L tau is not robust to random instantiation, then there is some no access distinguisher A, so that there is no algorithm for learning a Q tilde that is even no access indistinguishable from tau of P star. So in the last couple of minutes, I want to tell you a bit about the intuition for how to prove this. So the exciting case for me is sufficiency. So suppose you have a whole bunch of samples from real life, xi, oi star. Take your samples and we're going to partition them. Now, remember, these are real life samples. So the oi stars are Boolean. And in a strong sense, we can look at a bunch of samples and say, oh, yes, these are in fact samples from a particular random instantiation of P star. That's what that Bernoulli draw is. So we can break our sample collection into L partitions, and we can view the first set as samples from one random instantiation and the second set as samples from another random instantiation, and so on and so forth. So we have samples from L different random instantiations. Now there's a tiny technical detail here about what happens if a feature vector appears twice in our collection, but that's so unlikely that I'm not going to talk about it. But you know, it means you have to add a negligible to all of the analyses. Okay, so we have samples from the first random instantiation, second random instantiation, third, and so on and so forth. We run the learner independently on each one of those, and that gives us parameters pi 1, pi 2, pi j, and so on up to pi l. So now, given more samples from real life, we're going to show how to use these pi's that we've learned to build samples for something that's very close to Q star. So given a sample xy, we're going to uniformly choose a j from between 1 and L. So we're going to choose one of these pi's, and we're going to output the pair xz, where z is drawn according to the Bernoulli distribution that has parameter tau sub pi j of pj of x. So we learned pi j. Given pi j, we now have a transformed predictor, tau sub pi j of pj, and so now we have a sample from there. So y, when we have this pair xy, y is a random instantiation of p star of x. And so again, we're setting pj of x to equal y, and we evaluate tau pi j on xy to obtain tau pi j of pj of x. Okay. So what does that say? Because of the way we chose j uniformly at random, xj is now just a sample from this distribution, the expectation over j uniformly in L of tau pi j pj of x. And now we use robustness to say that we have a sample, you know, basically we have samples from this term here on the right. And by robustness, we know that that's approximately equal to tau p star of x. So if L is large enough, then we can just use Chernoff bounds to say that we're getting something that in X is very likely to be very close to, in expectation, tau p star of X. So we have a way of generating things that are very close to samples from Q star. So that's the positive direction. The intuition for necessity it's kind of more mysterious in some ways. But the idea is that if tau is not robust to random instantiation, then by definition, there's a p star and a large set of elements x for which there's a big gap between tau of p star of x and the expectation for random instantiations of tau of the random instantiation of X. And we use that S to define a level 1 distinguisher. So, to my knowledge, this is the first work in the rapidly expanding OIMC literature that considers prediction for a better world. And we have a complete characterization for when that's possible and an algorithm. So the question is, what would we like to do next? And one thing is to develop an understanding of what it is that robust transformations can accomplish. And another thing that we can do is we can create a sort of holodeck. We can use the technology to explore proposed transformations that we are considering and see what would their results look like. Okay. Thank you.
Questions?
So I had a question regarding the necessity condition. Do you have a conceptual interpretation of what does this large set of X elements mean, or like, especially for the transformation of just adding 0.2?
Good. So the fact that we get a difference of the kind shown here is immediate from the definition, from what it means to not be robust to random instantiation. And then we can define 2 random variables, which looks at like the expectation of Q tilde of X for X in S when Q comes from tau of P star or tau of P star versus from an expected over P prime of tau of P prime. And they have to have, and these 2 random variables have to have nearly identical distributions. But if multi-accuracy were actually possible, then they would have to have different distributions because of this gap. So we get a contradiction, and the contradiction comes from the way we define the random variables and the way we get our hands on their values via multi-accuracy. So it's a pretty I don't know.
Okay. Another question. Thank you for your talk. I was wondering, and I think you're maybe getting to it with the last slide of next steps, but I was trying to kind of understand how we're supposed to think about using this Q tilde. And at least based on my understanding, it's not something we should deploy immediately. Like, we have no guarantee that deploying it will get us closer to this better world. It could potentially even bring it further away. So what you're saying is we should kind of use it to explore what world these transformations are bringing us to?
Interesting. So what I said earlier was that, we're going to assume that we have reason to believe that Q star is a better world than P star. And so we would want to be able to model Q star, and therefore we would want to be able to build this Q tilde. Now, your question is great. Sometimes I think that people have enough understanding to know that if they change things a certain way, then the world really will get better. Let me just give it, for me, is a personal motivating example. I was in the first graduate class at Cornell, PhD student batch at Cornell, that was a third women. And the women in my year did really, really well. And I'm convinced that this is because we had reached a critical threshold, that we had critical mass. And I think that if you have an understanding of these kinds of phenomena and you use that to define your transformations, you will literally implement a better world. You'll get to a better world. Even the nasty work environments could be, the nastiness could be mitigated by having many more members of a minority group. Right? But having said that, I think that I really mean also my second bullet, which is to sort of like say, well, here's a proposed transformation. What would happen if the world looked like this proposed transformation? Let's study that and see whether we like it or not.
Thank you.
Last quick question or? Okay. Thank you very much, Cynthia, for joining us. For the talk.